participate in this event. And so I will start to share my screen again. I think it will work. So let me just.
It's perfect. We see it.
Yeah, but I think yes. So now it's really full screen, so it should be still slightly better. So yes, thank you again for the introduction and the possibility to give this presentation on my work, joint work for the most part on zero-sum sequences with weights. In part, it's joint work with Lou Selima Marchand, who is present in the audience. And in the end, I might also talk about more recent work with my colleague Oscar Ordasch, who is present here, on applications to factorizations of norm of algebraic integers of these zero-sum sequences with weights. And in the middle of the talk, I will also talk about interactions with coding theory. And in this part, I will also recall some general aspects of coding theory, so to say, to give some context. So what are these zero-sum sequences with weights all about? The main context in which these zero-sum problems studied finite abelian groups. So one considers a finite abelian group, something like the integers modulo some n, so say z modulo 7z. This would be a finite abelian group with 7 elements, and then one considers a sequence of elements in this group. A simple fact is that if the sequence is very large, then I can find a subsequence whose terms sum to 0. And why is this the case? Well, it's some kind of pigeonhole principle argument. So I consider all the sums, and that I always add one more element, one more element, one more element, and then at some point I get a collision. And then I take everything between the two collisions, and this necessarily sums to 0. Or another way to see this would also be, I mean, if the sequence is really long, then some element has to be repeated very often. And then I just take this element, its order many times, and this also sums to 0. So just to see that it is finite is rather straightforward. But an interesting question arises, namely one which was asked by Davenport some 40, 50 years ago. What does this sufficiently long mean exactly? So what is the precise threshold? Give me a finite abelian group. How many elements, repetition allowed, do I need to consider to find a subsequence that has sum 0? And one can also modify this problem. For instance, one can impose a restriction of the length on the length of the sequence. This was done by Erdős, Ginzburg, and Ziff. Also, one could study sets instead of sequences and do various other variants of this. And all these things are studied, but let's stick with the classical problem of the Davenport constant and its immediate variance. So a formal definition of the Davenport constant would be the smallest integer L, such that each sequence G1 up to GL over G has a non-empty zero-sum subsequence. So some collection of indices such that the sum of the corresponding terms just equals 0. Equivalently, this would be 1 larger than the maximal length of a so-called zero-sum free sequence. And a sequence would be called a zero-sum free if it does not contain any subsequence whose terms sum to 0. And again, equivalently, it would be the maximal length of a so-called minimal zero-sum sequence. So a sequence whose terms sum to 0, but for no proper subsequence, the terms also sum to 0. And these problems are studied since 50 years, and there are various applications to number theory on Carmichael numbers and factorizations of algebraic integers. And maybe I will talk something about factorizations of norms of algebraic integers at the end. also in graph theory, various applications. So these are well-studied problems. So what can one say about them? So by a classical result, every finite abelian group can be written as a direct sum of cyclic groups. So Cn1, this is a cyclic group with n1 elements. So basically set modulo n1 set. And so then I consider vectors of congruence classes if one wants. And so this is any finite abelian group can be written in this form. And then if one thinks about it briefly, what would be a lower bound for the Davenport constant, then one finds this expression which one see here. How can one establish this? Well, for each cyclic component, if I take an element which just has an entry of 1 for this one cyclic component and zeros elsewhere, and I repeat this, the order of this group -1 many times, then with this piece I cannot form 0, and I do this for each coordinate, and this gives a zero-sum free sequence of length sum I equal to 1 to r and I minus 1, and then I still have to add one more. So this is a relatively direct lower bound construction which was found right at the start, and it actually turns out that this is sharp for certain types of groups, for P groups, for instance, but this is subtle to prove. So it's well known by now, but one needs some algebraic tools to prove it. So one cannot prove it in a straightforward way. And then one can pass on to groups of rank at most 2 and show it there with so-called inductive methods that allow a reduction to P groups. And one can also show it in some other cases. So for certain groups of rank 3, for instance, there are some results. But also since early on in the series, so basically also right from the start on, Bayen found counterexamples, and then there were more counterexamples to an equality in this inequality. So this lower bound construction, which seemed so natural, it's not always optimal. And this also shows that this problem is really difficult, and as a result of this also there was not all that much progress in the last decades on this precise constant, because there were successes early on in the theory. One showed it for P groups, for rank 2 groups, but then if you look for rank 3 groups, I mean, it's not a complete list of results that I gave, but it's rather special, and in particular for groups of rank 3 in general, the problem is open. So one suspects that maybe for groups of rank 3, still equality always holds, but this is an open problem. And by contrast, one knows that for groups of rank at least 4, equality does not always hold. And here I gave an example of a group of rank 5 where equality does not hold, but one could give more complicated examples of a slightly lower rank. And even so, it's really then not clear what to expect exactly. Of course, one can have some general upper bounds. For instance, there is an upper bound of this form that for k not too large to the exponent, one always has this type of inequality, or one also has this general upper bound that the Davenport constant can be bounded by something exponent times logarithm of the order of the group over the exponent. So what is this roughly? So it's somewhat the rank times the logarithm of the group. So in some sense, one has a factor of a logarithm of the exponent too much for this upper bound. There are more recent results. I do not have them on the slide, but a colleague of mine, Benjamin Gerard, recently showed that asymptotically, in a certain sense, this is actually an equality for certain groups, but the exact values remain unclear. So now let me turn to these other zero-sum constants that I mentioned. So this was for the Davenport constant, where one just wants any zero-sum subsequence. And then I mentioned the problem by Erdős, Ginzburg, Ziff, where one wants sum exactly equal to the exponent. And then we can generalize it a bit with some j that is larger or equal than the exponent, and define a constant s less or equal than j, which is defined as the largest constant such that each subsequence of these given lengths is a zero-sum subsequence of lengths at most equal to j. This is actually well defined for the reason I mentioned earlier, because if I take a sequence which is very, very long, one element will be repeated very often, and then I take this element, its order many times, and this sums to 0. And the order is at most the exponent, and therefore this works out. And this is why I have this condition here that the j needs to be greater or equal than the exponent. Otherwise, I mean, I can define the constant, but also with a smaller j, but then it would just give infinity. So, and the case of j equal to the exponent is particularly well known, and this is called the eta invariant. And for exactly equal to j, this would be the so-called Erdős-Ginzburg-Ziff constant. So one can study these constants too. And now one has these constants, we'll come back to those. So I mentioned in my title that I will talk about weighted zero-sum problems. So, and these were introduced about a decade ago, by now more than a decade ago, in a series of papers by Adhikari, Balasubramanian, Chen, Friedlander, Konyagin, Papaladi, Rath. So also for a finite abelian group, one considers a set of weights. These weights, I mean, they are just integers, but they play the role of weights. So therefore a set of weights, but so a set of integers which will operate as weights. And then one introduces a so-called W-weighted Davenport constant as the smallest L, such that each sequence G1 up to GL over G, so this is the same, has a non-empty W-weighted zero-sum sequence. So this means that I can choose some factor here such that the sum is 0. So maybe I allow, if I take the set of weights equal to 1 and -1, then this would mean I can either add or subtract an element of the sequence, and this gives more choice, and so it might be easier to get 0. Or if I take the set of weights 1 or 2, then I can either add the element or add twice the element. And in the same way, one defines these other variants that we saw before. So this is one thing, weighted zero-sum constants. And there's another modification on zero-sum constants, so-called j-wise constants, and in particular we have the j-wise Davenport constant here. It's defined in the following way. So if the sequence is long, we have one zero-sum subsequence. If the sequence is still longer, then we will have several zero-sum sequences. So I can ask the same question that I had asked before, but now I impose for some fixed j, say j equal to 7. What is the smallest length that guarantees 7 zero-sum subsequences of this sequence? And I do not, and here one needs to be a bit careful. What do I mean by having 7 zero-sum sequences? And I mean, so to say, 7 at the same time, so really disjoint sequences. So I do not take the sequence and I say, okay, here I have a sequence, then I put it back and I look for another, but rather in the other way. So I take away one zero-sum sequence and then I take away another and still another, and I want to be able to extract 7 zero-sum subsequences. So if j is equal to 7. And this question was raised by Halter Koch in the beginning of the 90s, and here the question is, what's the exact constant here? And this is an interesting constant for various reasons. Some because of applications in algebraic number theory, but also for intrinsic reasons in zero-sum theory. And so this is a result by Delorme, Ordosh, and Quiros. They showed that if we have a finite abelian group and H a subgroup, then I can bound the normal Davenport constant by this j-wise Davenport constant, where I take the j equal to be the Davenport constant of the subgroup and take it of the factor group. And so this is this inductive method that I mentioned before. So it allows somehow to induct by subgroups. So if one understands the Davenport constants and these j-wise Davenport constants for subgroups and quotient groups, then one can obtain information on the Davenport constant by combining these. So this is a motivation for considering these j-wise constants. And these constants are also known for groups of rank at most 2 and closely related situations to these. The groups of rank at most 2, these are results by Halter-Koch, Delors, Morder, Quiros. Yet in contrast to the standard Davenport constant, it's not known for general P groups. So there's really a discrepancy there. And it's not even known for elementary P groups. So elementary P groups, these are just copies of one group of prime order. It's known in special cases for C2 to the 3, for instance, for C3 to the 3, for other elementary 2 groups of low rank. And for all J, I mean, they are known in these cases, and for a specific J, in particular for J equal to 2, they are known for some more groups of the form C2 to the R, so elementary 2 groups. But it's, for instance, it's not known in general even for relatively not so complicated groups like C5 to the power 3. So it's not known in these cases, these constants. And so how large would these constants be? One can also modify, so to say, the lower bound construction we saw at the start, or also have some kind of abstract version of it to get bounds of this form. So if we fix a group and let the J grow, then it will grow like linearly in the exponent of the group. And this is actually sharp for groups of rank at most 2 and in some other cases, but this is a rather rare phenomenon that it is really always sharp. And an immediate upper bound would be J times the Davenport constant, but this is only sharp for cyclic groups and is just too large in general. But there is a modification of this, which is that one can bound this constant dj by J times the exponent of G plus this factor here. We recognize the eta constant from before, and this is sharp for groups of rank at most 2 and in some other cases, but rarely. But what one sees here, at least, so if one really fixes the group and lets the J grow, then it's like J times the exponent of the group. And then there is some constant to be determined. And so, for example, for C2 to the R, one has this bound. So, which is, if J is very large, it might be good enough, but if J is fixed and R grows, then this does not really tell much in this form. And so, some time ago, together with Alain Plagne, I set out to improve the constants here. And so what we found is this. And for J equal to 2, this result was already known to the Komloj and Cardona Srivastava in a different context. One has these bounds for sufficiently large R. So this is now asymptotics in R. So J fixed and asymptotics in R. So there's some gap between the constant and the constants grow. But this is very, you see, it's very far away from an exponential growth in R. So it grows much, or at least it does not grow like 2 to the R. It grows much slower. And asymptotically, what we get are these bounds. So if the constants grow in J, but more or less not even linearly in J, but one divides by a logarithm. And then we have, we have R times J, and then we divide by a logarithmic factor. So R times J would be just the bound of J times the Davenport constant, but we can improve by a logarithmic factor here. And this is not too far from the truth. So there's a gap here. So, but it's J log 2 log 2 J log J, and here we have 2. So there is a gap of 2, but I mean, of the constant 2, but the general phenomenon is, so to say, determined. And to obtain these results, we used results from coding theory. So after this introduction on zero-sum sequences, now I will switch, so to say, to talking a bit about coding theory. And I will now start somehow to talk about coding theory in general terms. So towards the end of this section on coding theory, I will come to the link to my results, how these techniques are used, but now it's a general introduction on coding theory. So the main thing, what is coding theory about? So there's sometimes a certain confusion regarding what coding theory even is in principle. So it's about storing and transmitting information safely and still efficiently. But safely in this case means safe, so to say, from natural disasters. And it does not mean safe from attackers, people that want to spy on us. So this would be rather cryptography. And so in particular, we want to be able to deal with loss of a part of the data used to transmit the information without losing the actual information. Or at least we want to know that the problem occurred. I mean, this can also be helpful. So for instance, assume you receive some information and you recognize it does not make any sense, then this is also helpful, because then you can maybe double check what was meant. And so one adds some redundancy to have some possibility to check. And so there's a certain natural inevitable trade-off between safety and efficiency. So either I can have a very redundant system that transmits a lots and lots of redundancy, and then I can safeguard against a lot of errors, or it's very efficient and I don't add too much, but then maybe I cannot correct too much. And one can also formalize this. I mean, it's intuitive, clear in a certain sense. So if I want to have a lot of redundancy, then I have to transmit a lot more information. And what type of information am I talking about? Well, in principle, all kinds of information. So text, images, voice, all kinds of things can be transmitted. But here I focus only on cases where we already have, so to say, digital data. So just zeros and ones, or maybe also letters from another alphabet. So maybe not just zeros and ones, maybe also just some other symbols. But I want to discuss how one passes from an image or from voice to digital data. So this is also, in some sense, part of coding series, source coding, but this is not something I will talk about here at all. So what I mentioned here is a little bit about error correcting and error detecting code. So roughly we store digital data in a less efficient way, but so that we can deal with a loss of part of it. And I don't talk about source coding. So source coding would be, so you have some image, and how do you store it at all? So this is also an important problem, but not something which I will talk about. So an example of an error detecting code is the international standard book number. So if you open a book, in particular a book published before somewhat before 2007. Now it was slightly modified, but it was in use for a long time. Then you find a standard book number, and here I more or less randomly choose two books that I had handy when I prepared the talk. So, and then I took the international book number from these books. So they look, there's some number. So it's somewhat structured, but the information is, so to say, in the digits, not in the bar. And it's a number, but here there's an X. So this is one. So why is there an X? It's maybe surprising. Could there also be an A or some other symbol? But either it's a number or it's an X. And what's the rough structure of this? Well, the first digit gives the language. Then it's about the publisher and the book itself. And the last one, this is a check digit. So the 9 here, this is the check digit, and the check digit can also be an X. And so you see, so this is a book in English, so it's 1. Then, and so whereas here I think 2, so it should be. This is a book in French, so it should be. Because of this the 2. So, and the check digit itself, it carries no information in itself. So the book is uniquely identified without this check digit, but it allows to determine whether it's a valid book number. And a first step, what one does with this, so there are 9 digits, one calculates S, this number, in the following way. One calculates 1 times A1, 2 times A2, 3 times A3, and so on until the end. And then the second step is find a check digit that if I compute 10 times this check digit and add it to it, then the result is divisible by 11. And this actually always works if I allow for the A10 not only the digits from 0 to 9, but also I allow 10. So then I compute in modulo 11. So I can always make sure that the result is congruent to 11 modulo 0. And the check digit is determined in this way. So whenever you open a book, then you can check if you calculate 1 times this plus 2 times this plus 3 times this plus 10 times this, then the result will be divisible by 11. For whatever book you take, which contains an ESBN 10 number, which was true for most books until, let's say, from at the beginning of this century, it was true for all the books. Now it was slightly modified, but there's still something along these lines. But it's always the case. So, and this is always possible if we allow also that it is 10 and this is Z and the X represents a 10. Then it works. So therefore there's an X there. And so if we take this number, then we compute it and it works out just fine. We compute it, and for the other example, it also works. And so if somebody gives you a number and says, yes, this is an ESBN 10 number, you can run this check and see whether it's a valid number or not. And this is actually used quite a bit for quite a number of such identification numbers in various ways. So to check if something is even valid, so that people cannot just make up something, for instance. But what is this good for? Well, it's really for catching errors, and in particular for this system, if we change one digit, we will see it, and also if we interchange two adjacent digits, then we will see it. So we can catch either of these errors. So maybe one of the digits is incorrect, or maybe there's a flip of two adjacent digits. So this is detected. And so these are almost all the errors that people make. So 90+% of the errors that people make in practice are of this form. So if somebody has to order lots of books and they enter these book numbers, then there can be an automatic check to make sure that there is no incorrect order. So if you want to order a book and then you enter a number which is incorrect, then the system can alert you right away that there's an error and you can double check. And this catches lots and lots of errors. By contrast, if you enter a number and nothing is signaled, then it's not clear what you wanted to do. And of course, it would be inconvenient to order the wrong book. But if you by chance enter a valid one, then you are out of luck. But at least lots of errors can be caught by this. And another classical example would be the original ASCII code, which only contained 128 symbols and not 256 symbols. And the last bit was used as a check bit. So the last bit was added in such a way that the number of bits was always even. And so this also allowed to catch errors. So it was added one bit, which was redundant, but so that the number of bits was always even. So if one bit changed, then one also could detect it. Maybe since the time progresses a bit, I will skip this slide, because otherwise I will not come back to this. So let me skip this. So we have now a system in place that allows to catch errors. So to say, and if one wants to formalize things a bit, then an idea is if I have a string of bits and I have the idea maybe an error occurred, and I know strings which would make sense, then what do I do? Maybe I assume that few errors were made. And so I pass to the string. If I receive something which seems invalid, then an idea could be I pass to something that is valid and that is closest to this string that I actually received. And to formalize this, one introduces the so-called Hamming distance, which is defined as the number of bits that are different between two strings. So if I have two strings here and they differ in 3 positions, then I say the Hamming distance between these two is 3. And so if I want to encode k bits, this gives a total of 2k possibilities. So we need 2k valid messages or code words. And completely abstractly, a code can denote just whatever subset of 2k elements of some larger space of, say, n-bit strings. So if 2k words to encode, and I give myself n bits to do this, at the minimum I would need k bits, but I add some margin to have the possibility to correct errors. And then I can, in some sense, I can take whatever subset I want, but this is not very useful. So this is not what one usually does. And often the question is, what then would be a good choice for this subset? And one approach, one thing one wants is that the distance, this Hamming distance between different valid messages is large, because then I have a large distance between valid messages. And so if I just make a few errors, then I will still be close to a unique other message. And in this way, one can detect and even correct errors. And so this is the so-called minimal distance of a code. So one considers the minimal Hamming distance between any two words of the code. And then one can show that if the minimal distance of the code is d, then the code can detect d-1 errors, or it can correct d-1/2 errors. And why is this the case? Yes, because if I only change d-1 bits of a valid word, then it cannot be another valid word, because the minimal distance between two valid words is d. And so if I only change d-1, I would receive something invalid, and I can detect this. And so if I receive something invalid, I know there an error occurred. And I can also say instead, I correct d-1/2 errors by just, I receive something, it's invalid. So I assume it's what's closest to this. But this is another possibility to approach the problem. And then I have the following concept. So the n, so this is the length of the code. The k is the number of the words, 2 to the k is the number of the code words I have, and d is the minimal distance. And now there is some balance to be found, or one cannot have arbitrary choices here, of course, because if n and k are very close, the minimal distance cannot be too large. And so if we fix n and k, the larger the minimal distance, the better the code. In practice, that's a bit of an oversimplification, because also, I mean, the thing has to be somewhat viable to use. The question now arises, what is actually, how are these values n, k, and d related? And I will proceed here also a bit more quickly. And now I pass to linear codes. At the level of generality, which I just discussed, so we take whatever subset of ft to the n. This is a bit difficult to analyze, and what one often does is that f to the n is a vector space, and one takes for the codes a subspace. So this is then called a linear code. And then one considers a subspace, whatever subspace C, and the elements of these are the valid messages. And one then calls this an NK binary linear code, so of length n and size k. So n are the number, so to say n is the length of the string itself, and k is the size of the subspace. So if we go back to our ASCII example, the length of the code would be 8, because a byte is 8 bits, and the subspace would be the space of all the strings who have an even number of ones. So, and the minimal distance of this code would be 2. So for a general code, to determine the minimal distance requires to compare all pairs of code words, but for a linear code, it's more convenient. One just has to, one can consider the distance just to 0, and then introduce the notion of the weight of the code, which is the weight of the code is the number of ones in a code word, and one considers the minimal weight of all the non-zero code words. And here is an important point. Sometimes this causes confusion because, well, here one has an n-dimensional vector space and one considers a k-dimensional subspace. And one could ask, well, but this is strange because I know all the subspaces, they are the same in the sense that they are isomorphic. But still there are different codes. So why are there different codes? So because it's not really, it's not just a vector space and a subspace, but I have a distinguished basis. So in a more algebraic terms, one doesn't just have a vector space in the subspace, but one has a vector space with a fixed basis, and then one considers subspaces. And therefore there is, and then not everything is the same. And related to this, for subspaces can be described in some sense in 2 ways. Often subspaces either describe the subspace as the image of a linear map from so I can consider f2 to the k, and then I can have an embedding of f2 to the k into f2 to the n. This is one possibility. Or and this would be a general, then I take some matrix and multiply all the elements of f2 to the k, which is matrix G, and then get a subspace of f to the n in this way. Then one would call this a generator matrix. Or one does it the other way around, which is also common. One has a space and large space f2 to the n, and one describes the subspace as the solution of a system of linear equations. This is also what one does often in a geometric context, in a linear algebra course. So one has a plane which is described as the set of solutions of a system of linear equations. And in this case, this is then also a matrix. In this case, one calls this matrix a control matrix of the code, or also a parity check matrix. So for instance, for a particularly simple example, if one has a so-called repetition code where one repeats everything 3 times, then the parity check matrix would look like this. For this SC code with parity bit, so this would be an 8-7 code, as I said, and then the parity check matrix would be just one repeats, the control matrix, the parity check matrix would be just one, would look like this, so just all ones. And if one multiplies this with some vector, then it's 0 if it has an even number of ones, and 1 if it has an odd number. So now, after this introduction on coding theory what's actually the link to my zero-sum problem. So the link is that if I have a sequence in a finite abelian group in an elementary that is even in an elementary 2 group, then I can consider these elements also as vectors. So to say, I can consider this as a vector space over the field with 2 elements. And then I can say that the sum of a subsequence here, this is equivalent. So I write these coordinates of each element as the columns of a matrix. And then I can say the sum is 0 if and only if, so to say, this matrix times the vector gives 0. So thus G1 up to Gn has a zero-sum sequence of lengths at most d if and only if the minimal distance of the code with parity check matrix, this matrix, has minimal distance at most d. So I can translate this problem on zero-sum sequences in a problem into a problem on codes. And then one has, so then I can study more or less this constant Sj, S index J using codes. And if I want to study these J-wise constants, then there is even a notion in coding theory of so-called intersecting codes, where one studies codes where the support of code words, so this is the positions where there is a 1 bit where they always have a non-empty intersection. So this is a notion considered in coding theory, and one has an equivalence established by Cohen and Seymour that to determine the size of for which nk intersecting codes exist is essentially equivalent to determining this 2-wise Davenport constant of C2 to the R. And so now going back to the upper bound that I had, so the Laurent Mordech-Quiros established the following, that dj1 plus g can be bounded in the following form using the earlier j-wise constant plus and the maximum of this constant where one has a zero-sum subsequence of size at most I. And so if one wants to apply this, one needs knowledge on these constants Si. And I introduce here some ad hoc terminology. So if we call this an upper bounding function or an asymptotically upper bounding function if this bound holds for any binary linear code. And a well-known bound in coding theory is the so-called Hamming bound, which can be formulated like this, where H is a binary entropy function. So, and then one has the following key lemma. So, when one has an asymptotic upper bounding function, then if one has this relation, then one gets a bound on this constant as the C to the R to the N. And the advantage of having this is that there are, in coding theory, many such functions were established. So one knows such functions and then can apply them. So how do we obtain our actual upper bounds? We use the result of the Laurent Mordech-Quiros to reduce to determining these constants, and we reduce determining this to bounds and codes, and then we use bounds from coding theory. So I did not detail this now, but I briefly mentioned it. There are really lots of works in coding theory which establish which functions are so-called upper bounding functions. And then we perform some computations to assemble, so to say, the pieces. And for the lower bound, this can be proved in some non-constructive way of Also, it can, in some sense, be seen as a probabilistic argument if one wants to do it, but maybe I'll skip this. And this is, well, a question would be, what is the true value? And we suspect more that it's towards the lower bound of our two inequalities that we had. And now, maybe to finish, I'll come back to the weighted Davenport constant. And so I gave the definition before. So here we have a set of weights, and we ask the same questions which we had before when we allow weights in front of the GI. And one can also introduce a multi-wise version of these constants, which we did together with Marchand, Ordas, Santos. And we focus here on the case of plus minus weights or weights of 1, 2 up to the exponents, which one sometimes calls fully weighted, but there are plenty of other options too. So if there is one has the following equivalency. So if there is an odd prime and I is greater or equal to 3 and n greater equal to 4, and one has elements of this elementary B group, and one assumes that the GIs generate CP to the R, so a generating set, and the following statements are equivalent. So this has no weighted zero-sum subsequence of length at most 3. The n minus R code with parity check matrix G1 to Gn has minimal distance at least 4. Or the set of points represented by the GIs is in the projective space of dimension R minus 1 over the field with B elements is a cap set of size n, that is, there are no 3 points on the line. So there is also a link of these types of problems to certain problems in discrete geometry. And here I should briefly say, so I cheated a bit here because here now one considers codes in a slightly more general sense than before. So it's not about over F2 anymore, but about over a field with P elements. And so in particular, the following integers are equal. So one can bound these zeros via bounds from coding theory. And one also here is the following equivalence, very similarly to above, for the set of, the set of weights is the full set of weights, then one has the link that there is a zero-sum subsequence, a weighted zero-sum subsequence of lengths, at most the if and only if the minimal distance of the code with parity check matrix G1 up to Gn has minimal distance at most D. And then one can show that this lower bound on the multi-wise Davenport constant in a similar way than in the group for elementary two groups, but some modifications are of course needed. And then we have also the following result, the upper bound, if P is a prime number, and we take this set. When m tends to infinity, then we have this upper bound. And excuse me, it should not be m, so m is equal to j. So, yes. And so this would finish the presentation of the part on zero-sum sequences and coding theory. And as you noted, there would be still 1 or 2 slides left for the link to factorizations of algebraic norms of algebraic integers. But if I see it correctly, I think towards the end of my allotted time. So I would stop here, and if you like, I can still say something on the algebraic integers, but I'll stop here for now.
Thank you, thank you. Bueno, si hay alguna pregunta. Repito, si hay alguna pregunta para el profesor, si no. Well, Professor Smith, it seems that we don't have any question now. Well, actually, I have a question, but it's a rather, outwork from your presentation. If I have one of such groups, the exam of some CNs, for example, C2 plus C3 and so on, and I have a geometric object which has such a group as a homotopy group. For example, I have two tori put together and the homotopy tie is C2 plus C2. And I find one of those zero-sum sequences. I wonder if I could somehow get some information, see if the sequence could give me some information, some geometrical information of the object.
I'm not sure about homotopy groups. So to say, one application, one main driving force in the development of zero-sum theory was that one can study zero-sum sequences in the class group of an algebraic number field. And this allows to deduce information on factorizations of algebraic integers. But I'm not well versed in homotopy theory and algebraic topology, so I'm not familiar with links to this, but possibly they might exist. So this is something which one could pursue.
Mm-hmm. Yeah, actually, I don't even know if the question has any makes any sense at all. Maybe it does. It doesn't. I don't know. Okay, thank you.
Thank you.
De nuevo, ¿hay alguna pregunta para el profesor? Well, Professor Smith, we don't have any more questions. We want to invite you to the ending ceremony, which is going to be at 16 hours today. I don't know if it's convenient for you. Anyhow, you are welcome to join us to the ending ceremony and present you the certificate of participation.
Okay.
So,
I'm just
Hay una pregunta.
Can we read the question in the chat?
There is a question?
En el chat, profe, hay una pregunta.
The chat, yes. I'm asking which are the mathematical differences between cryptography and coding theory.
The mathematical differences between coding theory and cryptography, if I understood the question correctly. Well, I think the goals are already rather different in a certain sense. So in coding theory, one encodes information in such a form that that errors can be corrected, and in cryptography it should be so that it is secret and it cannot be retrieved. So a lot of coding theory operates in these finite dimensional vector spaces, at least the part with which I'm familiar with, and then one is in somehow in a discrete geometry setting, or sometimes one also uses tools from algebraic geometry and has certain surfaces that then give not necessarily surfaces, but so to say, one can, for instance, consider the points of an algebraic variety as the code and so on. So one is in this setting, and in cryptography, certain aspects in use number theory. So like the RSA method uses calculations, uses properties, uses algebraic number theoretic properties. For instance, also certain cryptographic schemes are based on the fact that the primitive the discrete logarithm problem is difficult to solve in various settings. But there are other aspects in both of them on a mathematical level, and there's also it's also possible to use codes, as I mentioned them, to construct cryptographic systems. So I would say a coding theory, in the way I mentioned it here, at least it's somewhat geometric in flavor. So it's somewhere between maybe a lot of, it's discrete of course, but there are geometric ideas often involved. And maybe this is less the case in cryptography, but it also really depends which type of cryptography. So maybe it's more number theoretic than geometric. But this is so to say a vague answer, because both fields are vast, and I have no expertise, so to say, to speak about all of it. And more or less there certainly counterexamples to what I just said. But I would say yes, maybe there's more of this geometric structure in coding theory than in cryptography.
Thank you very much.